In this video, we're going to talk about degrees of unsaturation. Degrees of unsaturation is also commonly referred to as index of hydrogen deficiency, or IHD. Compounds that are unsaturated or hydrogen deficient have fewer hydrogens. For example, because this molecule has a double bond, it has less hydrogens than the saturated version would have. Butane over here on the right has the maximum number of hydrogens possible, so this molecule is considered to be saturated. 2-butene over here on the left is missing 2 hydrogens, 8 versus 10, so it is considered to be unsaturated, or more specifically, it has 1 degree of unsaturation. We could also say that it has 1 IHD. In this example, a double bond is causing an unsaturation, but rings can also cause unsaturations. In these examples here, you can see 1 IHD caused by a double bond. Ethine has 2 pi bonds, so that is going to end up with 2 IHDs, or 2 degrees of unsaturation. As always, we're comparing to the unsaturated molecule. Ethane has 6 hydrogens, so loss of 4 hydrogens results in 2 degrees of unsaturation. Ethanal over here also has 1 degree of unsaturation, or 1 IHD. You'll notice that the oxygen here does not affect the number of carbons and hydrogens. Oxirane over here on the right has a ring instead of a double bond, so it has the same molecular formula as ethanal. Both of these have 1 IHD. They would also be considered to be constitutional isomers because they have the same molecular formula but different connectivity. Halogens replace a hydrogen, so anytime you see a halogen, you want to think of it basically as a hydrogen. You can see that C2H4 and C2H3Br both have a double bond. So they both have 1 degree of unsaturation, or 1 IHD. Amines, however, add a hydrogen. So this molecule over here also has 1 IHD, and you can see from its molecular formula that it's C2H5N as opposed to C2H4. To calculate degrees of unsaturation, you can look at the structure or you can look at the molecular formula. If you're looking at the structure, just keep in mind that each pi bond counts as 1 degree of unsaturation, and each ring counts as 1 degree of unsaturation. This method is fairly simple because you don't have to worry about halogens or nitrogens. You can just ignore them and count pi bonds and rings. If you like using this method, and all you are given is a molecular formula, you can just draw a structure that matches that molecular formula, and then count pi bonds and rings. If you have a molecular formula and you would like to calculate degrees of unsaturation from the molecular formula, first you need to determine the number of hydrogens in the saturated molecule. Subtract the actual number of hydrogens in the molecule, and then make sure to account for any halogens or nitrogens. For this method, I've developed an equation. This first part here is the number of hydrogens in the saturated molecule. You're taking the number of carbons times 2 and then adding 2. And this makes sense because in a long chain, you have 2 hydrogens on every carbon, except for the ends when you have 3 hydrogens. So that's what this first part is. Then you are subtracting the actual number of hydrogens, right here. If you have a halogen, you treat it like a hydrogen, so any halogens you would add in here. If you have a nitrogen, however, you would have to subtract a hydrogen. Remember that 2 hydrogens equals 1 degree of unsaturation, so of course you have to divide all of this by 2. We can apply saturation and unsaturation to biomolecules. For example, stearic acid here is considered to be a saturated fat. It is saturated because if you look at the carbon chain, we have no double bonds. Of course, there's 1 degree of unsaturation here, but for the purposes of fat classifications, we would consider this to be a saturated fat. An unsaturated fat, like oleic acid shown here, has a degree of unsaturation in the carbon chain. Oleic acid, shown here, also has a degree of unsaturation in the carbon chain. So both of these are considered to be unsaturated fats. Specifically, oleic acid is a trans fat because it also has a trans alkene. Keep in mind that for cis fats, carbon-carbon double bonds will lower melting points. You can see the examples here with oleic acid, linoleic acid, and linolenic acid. Oleic acid here has a melting point of 16 degrees, and it has 1 double bond. Linoleic acid has 2 double bonds, and now its melting point is lower at -5 degrees. Linolenic acid with 3 cis double bonds has a melting point of -11. Remember that this concept is related to intermolecular interactions. Molecules that have lots of intermolecular interactions will have higher melting points. By adding the cis double bond, we prevent some of the intermolecular interactions that can occur because now these molecules can't stack as nicely. Saturated fats thus have higher melting points, and so do trans fats, because they can stack better and interact better. This concludes Chapter 4. In Chapter 5, we're going to focus on stereoisomers.